All right, welcome back, everyone. So last time we covered our reliable TCP pipes and wrapped them up in those secure TLS shields. We've got a safe, dependable way to talk to a server. But there's a huge step we've kind of just glossed over. How do we find the server in the first place? And that brings us to one of the most fundamental, foundational pieces of the entire internet, which our source material covers in Chapter 4, Discovery, and the absolute magic of what we call the Domain Name System, or DNS. And this slide right here, this is the entire problem that DNS was invented to solve. See, we humans, we think in names. We remember words like google.com, but computers, they don't care about that. They operate on numbers, IP addresses that are basically like a street address, a specific coordinate on the vast map of the internet. The entire job of DNS is to be that universal translator between our human-friendly world and the machine-friendly world of numbers. Now, you've probably heard this 1,000 times, right? DNS is the phone book of the internet. And you know what? It's a great starting point. You look up a name, you get a number. Simple. But for us as back-end engineers, that's just the cover of the book. The real story, the how it all works under the hood, is an absolute masterclass in building distributed systems at a truly global scale. So from our perspective as engineers, this is the real definition. Let's actually chew on that for a second. Distributed means there's no one single computer holding all the answers. The database is spread all over the world. Hierarchical means it's structured like an upside-down tree, starting from an invisible root, then branching out to things like .com, and then branching again to specific domains like google.com. And that last part, eventually consistent, oh, that's the juicy part. That's the one we're going to keep coming back to. It means updates aren't instant, and that creates this fascinating and critical trade-off between speed and accuracy. Okay, so let's follow a single request on its journey. The moment you type a URL into your browser and you slam that enter key, you kick off this incredible chain of events. It's almost like a little dance that happens in milliseconds, completely invisible to you. So here's that dance, step by step. First, your browser checks its own pockets, its local cache. Have I looked this up recently? If yes, great, we're done. If not, the operating system checks its pockets. Still no? Okay, now the real work starts. The request goes to what's called a DNS Resolver, usually a server run by your internet provider. Now this resolver, it does the heavy lifting for you. It starts at the very top of that tree, asking a root name server, hey, where do I find anything about .com? The root server doesn't have the final answer, but it points the way, sending the resolver to the top-level domain server for .com. The resolver then asks that server, okay, great, but who's in charge of google.com? That server points to the final stop, the authoritative name server for google.com, which finally has the IP address. It gives that answer to the resolver, which caches it for next time, and sends it back to your browser. Phew. Now, here's a little security tip for you that's pretty wild. The original DNS protocol, it was built for speed, not privacy. So it sent every single one of those lookups in plain text over UDP. Just think about that for a second. Anyone on the same Wi-Fi as you, at a coffee shop, an airport, wherever, could literally see every single website you were trying to visit. It's a massive privacy hole. And that is exactly why the industry has pushed so hard for more secure options like DNS over TLS, which encrypts that whole conversation so nobody can snoop. Okay, but hold on a minute. That whole dance we just walked through, that involved multiple network requests hopping across the globe. If we had to do that for every single thing on a web page, every image, every font, every script, the internet would slow to an absolute crawl. It would be a total performance nightmare. So how on earth does this system actually work at scale? The answer, of course, is caching. Massive, aggressive caching at every single step of that dance. Your browser caches, your OS caches, and especially your ISP's resolver, it caches like crazy. This solves the performance problem brilliantly. But just like with everything else in system design, when you solve one problem, you almost always create a new one. In this case, the brand new problem is consistency. How do you make sure that all of these caches aren't holding on to old, outdated information forever? Well, the mechanism that governs this whole balancing act is the time to live, or TTL. It's really just a number, measured in seconds, that gets attached to every single DNS record. Think of it like an expiration date. It's a simple instruction to any cache that says, hey, you can use this answer for this long, but when that timer hits 0, you have to throw it away and come ask me again. And this right here, this slide perfectly captures a fundamental trade-off that we as engineers face all the time. On one hand, you could set a long TTL, say 24 hours. the performance is fantastic. Your servers get way fewer requests, users get lightning-fast lookups from their cache. But what if you need to change your server's IP in an emergency? Some of your users could be stuck trying to connect to a dead, ghost server for an entire day. On the other hand, you could set a short TTL, like 60 seconds. Now you've got incredible agility. You can redirect traffic almost instantly. The price you pay? You are absolutely hammering your own name servers with constant requests, and any user who gets a cache miss has to wait longer. This is the constant battle between consistency and performance that defines so much of what we do. And this brings us to the biggest danger of all. Because of this design, DNS is a massive single point of failure. Your application could be perfectly healthy, running flawlessly, redundant across 3 continents. But if your authoritative name server goes down and that TTL on all those cached records expires, your app just vanishes. As far as the rest of the internet is concerned, it no longer exists. We have seen massive internet-wide outages caused by this exact problem. So how do we design for this kind of catastrophic failure? Well, this is where we get a real pro tip from our source material, the principle of static stability. It's this core philosophy for building truly resilient systems. It basically says that your system should find a way to keep working, even if it's in a limited way, when one of its critical dependencies fails. For DNS, this means you stop treating the TTL like a self-destruct button. Instead, if a cache's TTL expires and it can't reach the name server to get an update, it should just serve the old, stale data it already has. And look at this. You can see exactly why static stability is so powerful. In a normal outage, the name server goes down, the TTLs expire, and resolvers start sending back errors. Your app is dead to the world. But with static stability, the name server goes down, the TTLs expire, but the resolver says, you know what? I can't get a new record, but here's the last one I saw. And guess what? That old IP address might still be perfectly valid. Serving a potentially working address is infinitely better than serving a guaranteed failure. This is prioritizing availability over strict up-to-the-second consistency, which is almost always the right call in a distributed system. So when you take a step back, the really crucial point is this. DNS isn't just some boring internet plumbing. It's a masterclass in how to design large-scale distributed systems. It's a planet-scale, real-world example of eventual consistency in action. It's a system that, by its very nature, prioritizes availability and performance over strict, immediate consistency. It forces us to balance those tricky trade-offs with tools like TTL. And maybe most importantly, it teaches us one of the most vital lessons in resilience engineering. Serving stale data is almost always better than serving no data at all. So, we've done it. We've used this incredible invisible map to find our server, and we have a secure, encrypted line to talk to it. But that just leads to the next big question, right? What do we actually say? How should we structure the messages we send back and forth? And that, my friends, takes us deep into the world of APIs, REST, and gRPC, which we are going to tackle in our very next explainer. See you then.